Hello, this is a short introduction on decision trees. My name is Þórður Víkingur. A decision tree is a graphical representation where we use symbols and branches to define every possible outcome impacting our decision. In this case, there are two designs to choose from. We can't choose both. We have to choose either electrical food processor or a gas food processor. As we have uncertainties, the designer estimates that there are 75% probability of success for the electrical design and 60% chance for success for the gas processor. The payoff for the electrical design is 10 million if success, but 3 million in loss if failure, and the gas design is 15 million in plus if success, but loss of 7 million if failure. This is the tree, and we have to say some words about what we see here. Now let's take a look at this. If you see the point there, this is a node or a decision node. The first node in the model or in the tree is called a root node. This, of course, are the branches describing the options, and we have added one more option, which is not to develop the product. Of course, that would result in no payoff, zero payoff. And if we follow the branch and go up to the circle, you see, a circle is a symbol of uncertainty. So you can see that there is a 75% certainty of success, meaning, of course, there are 25% certainty of failure or probabilities of failure. So there is uncertainty regarding the outcome, and this is actually the statistical distribution describing that uncertainty. In many cases, we will have more possible outcomes, and in some cases, you would have hundreds or even thousands of possible outcomes. But then you would use a simulator, usually Monte Carlo simulator, to deal with that type of problem. The payoffs, you can actually, if we take this branch, develop electrical power design, and it's a success, then we have 10 million in payoff. Or we develop the electrical power design, and it's a failure, we lose 3 million. So this is the tree. One more thing to add is that to calculate the expected value on the uncertainty node or chance node, we have to take the uncertainty into the account and the payoff. The uncertainty is described by this statistical distribution. It's very simple in this case. And we have to calculate the uncertainty or figure, to multiply the uncertainty times the payoff and sum up for all the branches. So the expected value for this chance node would be then 10 million times the probability of 10 million plus the minus 3 million and the probability of that outcome happening, and that results in plus 6.75. We do the same for the gas power design and receive the expected value of 6.2 million. That means, and in this case, we are looking for the highest profit, the highest payoff. In some cases, we are looking for the lowest. For example, if we are making a decision regarding cost, but in this case, we are looking for the highest payoff. So we choose to develop the electrical power design, and that will be your decision. However, the designer says, okay, let's say that we have a failure with either design. We could modify it, and the modified version could be a success. So he adds a new decision, or to the model or to the tree, and it adds estimates of success. So if we have a failure, the probability of successful modification that would bring money to the company is 30% in the case of the electrical processor and 80% in the case of the gas processor. So now we have what is called a two-stage decision, because first we have to decide what's design to choose, and then decide what happens if it's a failure and we go for a modification or not. So, and these decision trees can be quite complex and have many stages. So we begin by doing exactly the same as in the previous case. This is actually called rolling back the tree. So the first point is to take the probability of success and failure and take the expected value. That gives us minus 3.1, and then compare the minus 3.1 to the other option, which is the abandonment project, which gives us loss of minus 3 million. And that's a little bit better than the loss of minus 3.1. So we can actually, if you go this path, exclude modifying the design. We can simply forget about that. So we take the minus 3 million, and that will be the subject for the calculation of the expected value on this chance node. So we create that calculation. That's 10 million times the odds plus the minus 3 million coming from this place times the odds gives us plus 6.75. And we repeat the process for the gas power design. We get an expected value of plus 5.6 compared to the loss of minus 7. That's a no-brainer. We will modify the design, so the 5.6 we can exclude abandoning the project, forget about that. And expected value for this point is then 15 million coming from the success plus the 5.6 coming from the modified design, and that gives us 11.24 million in profits. And you can see now the case has certainly changed, because 11.24 is higher than the 6.75 and certainly higher than the 0. So now we would change our decision to the gas-powered design.